When we factor a polynomial, we always want to make sure that we are factoring the polynomial completely. That is, simplifying a polynomial down to its smallest and simplest factors. We have a strategy, which is laid out on the right side, of the things we want to look for as we are factoring down. And it's going to feel like we're going to have to keep checking these steps, but the unfortunate reality is that every time you factor, you might be creating another polynomial that on its own could be factored a further step. So we want to make sure we're always checking along the way. We're going to start with a relatively simple example of this and then build up to ones that are a little bit more challenging. So let's start with 4x squared y minus 16xy minus 20y. Our first check for any polynomial that we are factoring should always be the greatest common factor. You can see from these coefficients that our greatest common factor will include at least a 4. And then you see from the variable parts that we're also going to include a y. So our greatest common factor is 4y. Factoring that out of each one of the terms leaves x squared minus 4x minus 5. This parentheses, this polynomial, this trinomial that's inside the parentheses, is not a difference of squares, nor is it a difference or sum of cubes. There are 3 terms, not 2. So we can discount those strategies almost immediately. It's not a perfect square. While x squared is a square, 5 is not a square. Therefore, it's not a perfect square. So because it has 3 terms, we're going to try to use the AC method on it. We remember that if there's no coefficient in front of the x squared, that means my a is a 1. So my AC is negative 5, and then I'm going to look to sum to negative 4. I can do that by using x plus 1 and x minus 5. Now, really, I should check one more time to make sure that neither of these binomials can be factored any further. Obviously, they can't, so this is my final simplification. Trying another one, and this one's going to have to engage, we're going to have to engage a little bit more creativity on this one. 9b squared x minus 16y minus 16x plus 9b squared y. We look across the 4 terms and we don't see a greatest common factor. 9, 16, 16, and 9 do not share any common factors. And then if you look at the terms again, there's no variables, despite the fact that there are 3 of them that show up in all of the terms. So we can discount a greatest common factor. Difference of squares, difference of cubes, probably not going to work. We've seen some creative ways of using those in the past with more than 2 terms, but probably not going to happen here. AC method, perfect square trinomial. Again, no simplifying that can be done, only 4 terms. So grouping would be our next option. The unfortunate reality with grouping is if you look at these 2 terms and you look at those 2 terms, you're not going to see any factors in common. So grouping is a dead end. We didn't find a greatest common factor through the whole thing. We can't even find a greatest common factor through those pairs of terms. However, with a little bit of creativity, we can create a polynomial that actually can be. And you probably noticed right out of the gate that those 2 shared a coefficient and these 2 shared a coefficient. So while we have not engaged in this practice a lot, and we believed that factoring by grouping could work when there were 4 terms written in the order that they were in, sometimes we can get a little bit creative and we can rewrite the polynomial to actually create some factorizations by rearranging the terms, keeping the signs in front of everyone who had them, negative 16y, negative 16x, in the hopes that we could create something that could be factored. Looking at these first 2 terms here, we see a greatest common factor of 9b squared, which leaves behind an x plus y. If we want this to work, we know that we're going to have need at least an x plus y or a y plus x here, which is what we'll get out of the back parentheses if we factor out a negative 16. We're not alarmed by the fact that this says y plus x and this says x plus y. We know, thanks to the commutative property, that those are the same. So we have x plus y, 9b squared minus 16. You're about 3/4 of the way to the solution. There is one more step to take. We go back and we check our list, and we see that right here is the difference of squares. It's easy to miss, but it's there. So we're going to leave the x plus y as that common factor from the grouping step. And then we're going to use the difference of squares to factor that leftover polynomial. No greatest common factors down here. No more difference of squares. No more difference or sum of cubes. There's only two terms, so it's probably not a perfect square or an AC method. So we're down to our final polynomial simplification in that last line. In our third example, we're going to see something similar with rearranging the terms of a four-term polynomial, but to a different end. X squared minus 25a squared plus 8x plus 16. Now, at first glance, this may not look, again, like in the last one. I could take an 8 out of this back parentheses, which would leave me with x plus 2 as an attempt at a common factor, but there's no way that I'm going to create x plus 2 out of this front part. This one's a little bit different in that instead of trying to factor them off in pairs, we're actually going to look at three of them together. This one, and that one. Looking at those three individual terms and thinking about the three of them actually together, I shouldn't say individually, but together, we get a new polynomial that looks like this. We've regrouped those three together in the front. Instead of, again, looking at pairs, because this would feel like a difference of squares, this back half of the problem would feel like a difference of squares. This might have a common factor, but they're not really going to match up, so there's not a common factor to be taken. We instead look at those first three terms together. Looking at those first three terms together and ignoring the last one for just a moment, we're going to get back to how the fact that he's a square in a second. If we look at these first three terms together, we see that that's a perfect square trinomial. So we can factor those first three terms together as x plus 4 squared. Following that with a minus 25a squared. And now we have a difference of squares. But if you're thinking to yourself, well, a difference of squares requires two terms, we have seen a few examples where you can get creative with the difference of squares. And really, it just boils down to, do you have a square minus another square? And in this case, we do. So we're going to have x plus 4 plus 5a and x plus 4 minus 5a. So a little bit of creativity with factoring by grouping, thinking about the terms a little bit differently, creates for us a factorization that we would not have seen. This would have felt like it was prime. There would be nothing else that we could do to that polynomial. So a little bit of rearranging, a little bit of creativity with the difference of squares gets us to something that we can factor. Lastly, what I think is the most challenging example that we're going to see in this video is actually the one that involves the least number of terms, and that is the polynomial 3x to the 10th plus 3x. Looking at these two terms, we see a greatest common factor of 3x. So we're going to begin by removing that common factor, leaving us with x to the 9th plus 1. X to the 9th plus 1 is a sum of cubes. This is the cube of x to the 3rd. 1 is the cube of 1 cubed. So our next line is going to factor that binomial into the binomial-trinomial combination that we know from the sum of cubes. X cubed plus 1, x to the 6th minus x cubed plus 1. Again, making sure that those signs match, but that one is different. We check here, and we see another sum of cubes, so that can be factored a little bit more. X to the 3rd plus 1 becomes x plus 1, x squared minus x plus 1. That's just the factorization of x cubed plus 1. We look at this back trinomial that we haven't dealt with yet. It's a 3-term polynomial inside that parentheses, so I feel like we could go perfect square, which it's not. We also could go AC method, which is not going to work. The AC would be 1, and then you would look for a sum of -1, which is not going to work. We could check. We were allowed to check that because of the relationship between those two powers, but since it doesn't factor in any way that we have, x to the 6th minus x to the 3rd plus 1 gets tacked on to the end. So thinking about these 4 different examples, you saw a lot in here, a lot of different types of factoring in each one of these examples. So in this one, we saw sum of cubes from a greatest common factor. Here we saw a perfect square trinomial mixed together with the difference of squares, but it came from a grouping situation. Here we have a grouping situation that turned into an extra difference of squares after we rearranged the groups so that we could actually create a factoring by grouping. And then back here we had a classic AC method right after the greatest common factor. So a lot of different options come up when you factor these. So you really do have to use that checklist to make sure that you're covering each one of the steps, because you don't want to leave behind any factors that can be factored just a little bit more.